Hi Year 13, welcome to your introduction videos for this week. This is what we're going to learn, so we're going to try to extend our knowledge of working with vector equations of lines, and also I'm trying to understand what a plane is and how we can represent a plane with mathematical equations. Okay, so we're going to look at finding the shortest distance between a point and a line. Finding the intersections of two lines, okay, finding the shortest distance between two skew lines, and we're going to understand what a plane is and show all the ways that we can represent them with equations. Okay, so a lot to get through this week, so I need a lot of work, a lot of dedication. Okay, now to start off with just a little starter activity that's going to help us build into some of the more complex stuff this week and next week. This is a type of question we learned quite a long time ago in, probably early year 12. Now I want you to have a go at it yourself, but I just want to change part B because there's an aspect of that you won't be able to solve. So it says find the real value of the parameter k such that this system of equations does not have a unique solution. This is in the case where the system has infinite number of solutions, find the value of p and the solutions. So I don't want you to do that last bit of it because you're not really, I haven't taught you that. But I would like to, basically would just like you to find the value of p that would give you an infinite number of solutions. I suppose the value of p that goes with the value of k to end up with an infinite number of solutions. Hopefully you'll understand what that means as you go through the question yourself. So stop your video and have a go. I'm just going to clear some space. So I've got room. Okay. Let's just do this. Draw. Sorry, you can just skip past all this. Okay. Right, so how do we do it? We just got to basically try and solve this system of equations. And what I'd be looking to do here is eliminate x's and y's because you've got a k that goes with the z. So we're going to want to keep the z's and have a look at what equation that gives us. So how do we do that? Well, I suppose what I can do, is there anything I can eliminate straight? I can eliminate y straight away. If I call this equation 1, this equation 2, if I do equation 1 plus 2, what will I get? I'll get, if I add them, I'm going to get 4x, y plus minus y, that will eliminate them, plus 3z is equal to 4. Let's just call that equation 4 for clarity, and we'll call this one equation 3. So now I'm looking at 4x plus 3z equals 4. What about another equation where we eliminate y? I think perhaps what I could do is I could times equation 2 by 2. Let's times equation 2 by 6. So let's do equation 2 times by 6. We will get 6x minus 6y plus 12z equals 18. Okay? And then let's pair that off with equation 3, which is 2x minus 6y plus kz equals p. And what I'm going to do is I'm going to subtract these equations. So I'm going to get 4x plus 12 minus kz, let's just factor that out, okay, is equal to 18 minus p. Let's call that equation 5. Okay. That's nice because it's going to allow me to eliminate x's from equation 4 and equation 5 by subtracting them from each other. So I'm going to get 12 minus k z minus 3z is equal to 18 minus p minus 4. I've just done equation 5 minus equation 4. Okay? And so, again, factoring out z's, I will get 12 minus k minus 3 is going to be 9 minus k z is equal to 14 minus p. We're now in a position to actually answer this question. Because if there is no solution to this equation, it means that z has no solution in this equation. And hopefully you can see it. Let me just change colour here. That if the left-hand side here, if I get 0z, well then I'm not getting, if 0z is equal to something, positive or negative, then I'm not ending up with a real solution. So if k equals 9, there is no unique solution. There is no unique solution. Now, what I've said there is not strictly true. There is actually one case where there are solutions if k is equal to 9. And that would be if p was equal to 14. So what we're saying is, if k is equal to 9 and p is not equal to 14, then there is no solution to this equation. Now, if k is equal to 9, there is no unique solution. But if k is equal to 9 and p is not equal to 14, then there is no solutions at all. Okay? But if p does equal 14, then basically on the left-hand side, and k equals 9, you're getting 0 equals 0. Well, what that means is there's infinite solutions. Okay? If you're getting 0 equals 0, it means there are infinite solutions. So that answers both part A and part B. Okay? Part A is saying that if k is equal to 9, there is no unique solution, and most likely no solution at all. But if k equals 9 and p equals 14, there are infinitely many solutions to this system of equations. Okay? Now, I hope that makes sense. You really, really, really need to understand this. Yes, for this week, but primarily for actually what's coming next week. Okay, so if you're not sure the interpretation of these results, then please ask and I'll be happy to explain it more carefully. Okay? Right, anyway, let's move on. So, what we're moving back to the idea of vector equations of lines. Okay, and we've got a question here. So we've got a point P at -1, 2, 3, and a line with parametric equations. X equals 1 plus 2t, y equals -4 plus 3t, z equals 3 plus t. It says find the coordinates of the foot of the perpendicular from P to the line. Now, remember what I said, whenever you're doing a vectors question, you need an effective diagram. It doesn't need to be a good diagram, it needs to be effective. So here is a coordinate axis that we can sort of pretend is three-dimensional. As I said, we don't need to draw it three-dimensionally. And what we've got is we've got a line, so let's just draw a line. And we've got a point P. Let's draw a point P. It says find the coordinates of the foot of the perpendicular from P to the line. Now what does that mean? It means if I draw a perpendicular line from P to the line, it wants to know what that coordinate is going to be. That is what the question is asking. Notice that part B says find the shortest distance from the point to the line. Let's call this point A. Well, it's just going to be the distance of AP, because the shortest distance is going to be if we move in a perpendicular fashion towards the line. So it's helping with both questions. Okay? So what we've got to, first of all, part A is asking me where is that point A, and part B is asking me what is the distance AP. Okay? So how are we going to find out what a point A is? Okay? Now the first thing we need to know is what the direction vector of this line is. And hopefully, because you've done your learning from before, and it's sort of a few weeks before since you've done it, you've got x equals 1 plus 2t, y equals minus 4 plus 3t, z equals 3 plus t. Then the direction vector of this line is going to be 2, 3, 1. Effectively, the coefficients of t in the parametric equations. If you don't understand why that is, you need to ask. It's vitally important that you understand that. Okay, so we know that. What we also know is that this direction is perpendicular to 2, 3, 1. Okay, so what do we know about perpendicular vectors? We know that their dot products are equal to 0. So if I just say 2, 3, 1, dot AP must be equal to 0. Okay? So all I need to do is try and find out what the direction vector, what the vector AP is. I would like to know AP. Now, AP is equal to OP minus OA. There's that very important formula again. OP we already know because it's at the point minus 1, 2, 3. So that's going to be minus 1, 2, 3. OA we don't know because we don't know where OA is, but I do know that it is an arbitrary point along the line. So I can say that it's the point 1 plus 2t, minus 4 plus 3t, 3 plus t, where t is some value to be found. So let's do that subtraction. So minus 1, that's going to be 2t minus 2. 2 minus 4 is 6, that's going to be 3t. Oh, sorry, no, that's going to be minus 2t minus 2. And it's going to be minus 3t plus 6. And then 3 minus 3 is nothing much. That's going to be negative t. So we found AP, the vector AP, in terms of t. So now what I'm able to do is I'm able to substitute that into this equation here. Okay, minus 2t minus 2, minus 3t plus 6 minus t is equal to 0 because we know that those vectors are perpendicular to each other. Okay, so I'm just going to clear some space. If you need to see some working out, you can just go back in the video. Okay, so I'm going to find this dot product. Let's just change colour. So I need to do 2 times minus 2t minus 2. That's negative 4t minus 4 plus negative 9t plus 18 and then plus negative t is equal to 0. So we now have an equation in t that we can solve. So what's that? It's going to be negative 14t plus 14 equals 0. So 14t equals 14, t equals 1. So we know the point A happens when t is equal to 1. So I can now find out the coordinates of A by substituting t into the x, y and z. So my x value is going to be 1 plus 2 is 3. My y value is going to be minus 4 plus 3 is negative 1. My z value is going to be 3 plus 1 is 4. So it's 3 minus 1, 4. Okay, so that means the coordinates of A is 3 minus 1, 4. Okay, so I'm just going to write that in now. That's 3 minus 1, 4 for A. And P we already knew was minus 1, 2, 3. Okay. So, let's just delete everything now. What is the shortest distance between the point and the line. Well, now that I know where point A is, I just have to work out the magnitude of AP, right? So let's just do AP, which is OP minus OA. So it's the magnitude of OP's minus 1, 2, 3, minus 3, minus 1, 4, which is equal to minus 1 minus 3 is minus 4, 2 minus minus 1 is 3, 3 minus 4 is negative 1. So it's going to be equal to the square root of 4 squared, which is 16, plus 3 squared, which is 9, plus 1 squared, which is 1. So it's going to be the square root of 26. So there is the answer. The shortest distance between the point and the line is root 26. Okay, so we've answered the first part of our objectives for this week, which is finding the shortest distance between a point and a line. Okay, please let me know if you've got any problems with that.